And we can pass to the second speaker, Flavio Nicoletti.
Hey, hi.
You can share your screen, and in the meanwhile, I'm going to present me. Flavio is currently working at the Chalmers University of Technology in Göteborg, and he got a master thesis in 2018 in Rome with Federico Ricci Tersenghi on long-range circulation in one dimension. And in 2023, we got a joint PhD from Sapienza and Paris-Saclay, working with Federico Ricci Tersenghi and Silvio Franz. And after a postdoc at Sapienza, he has now a postdoc in Göteborg with Stefano Sarao Mannelli on statistical physics for machine learning. And today, Flavio is going to give a talk with the title Low Energy Excitations of Vectors in Glasses. Okay.
So, hi again, and thank you so much for the invitation for giving a talk at Young Seminars. So, I will talk you about results mostly by my PhD. And these results were done in collaboration with my supervisors, Federico Ricci Tersenghi and Silvio Franz, with Professor Giorgio Parisi, and Dr. Cosimo Luto, and the PhD student Luca Maria Del Bono. So, the outline of my talk is as follows. I'll start by motivating the work and giving some context. And I'll discuss why we choose this particular model of vector spins, and then we'll test this model as a proxy for glassy excitations in two different mean field settings. We'll consider first a fully connected network, and secondly, a random regular graph, so a sparse tree-like network. The motivation behind my PhD project was to try to understand through a first principle theory, such as that of spin glasses, more about low energy excitations in glasses. So it's been established by recent evidence, numerical evidence, that glass excitations are very different from those in crystals. It was observed late in the 70s that glasses at low temperatures feature an anomalous specific heat, scaling linearly instead of cubically in temperature. This feature was related to the presence of an excess of low energy modes. Later, in computer simulations of small computer glasses, it was observed that beyond the lowest phononic frequency, there are low energy excitations that are quasi-localized in space, non-phononic excitations that are quasi-localized in space, and feature a non-trivial exponent in the density, in the lower tail of the density of states. And the value of this exponent is still debated in literature. There are people that claim it has the universal value of 4, that can be derived from the phenomenological soft potential models. So soft potential models which treat locally a glass as a collection of anharmonic oscillators, whereas other evidence instead hints towards the system-dependent exponent. So the first goal of our mean field theory should be to see if it's able to reproduce the first two features, that is, a density of state that extends down to 0 frequency and localized soft modes. A second aspect that is important for our theory is that the theory should be able to describe the transition from a stable glass to a marginal glass. So marginal glasses are systems that exhibit extraordinary sensitivity to microscopic perturbations. They feature phenomena known as avalanches, where macroscopic changes in the system configuration can be generated by a very small local perturbation. So an example of a marginal glass is a jump configuration of spheres. Now, in mean-field models of these marginal glasses, the quantity that signals the marginal stability is a diverging nonlinear susceptibility, or also known as spin glass susceptibility. This quantity, in a thermal case or at zero temperature for thermal systems, can be related directly to the Hessian spectrum, the potential energy Hessian spectrum. In particular, the lower tail of the distribution of eigenvalues, close to zero eigenvalue, control the stability of the system. So stable glasses will be characterized by a spectral density featuring a convex power law close to the origin, whereas marginal glasses will be characterized by a spectral density featuring a concave power law close to the origin. So our mean-field theory should be able to describe the transition from a stable to a marginal glass. Now let's discuss why we choose vector spins. So first of all, spin glasses are, for those who don't know very well this model, are toy models for disordered magnetism, where a system of Ising spins interacts with random quench disorder interactions and eventually are subjected to the action of external magnetic fields. The most studied model in the family of spin glasses are either the sharing topic packet model in the fully connected case with Ising spins, or the spherical spin glass with p-spins, which instead is a good toy model for the glass transition in the random first-order transition description. Now, both these models, unfortunately, are inadequate for our purposes. Okay, this SK model, very trivially, because it's a discrete model, so it cannot feature any linear soft mode. And in addition to that, another problem of this model is that its critical line, also known as the Almeida-Towles line, is divergent in the zero temperature limit. So it's not possible to have a thermal spin glass phase transition. As to the spherical p-spin, its main problem is given by his Hessian, because his Hessian in the thermodynamic limit is a random matrix that can be drawn from a Gaussian ensemble of random matrices, or Gaussian orthogonal ensemble of random matrices. And so, by definition, this kind of ensembles cannot feature any localized modes, since it's a rotationally invariant ensemble. Vector spin glasses, as I will show you during this talk, instead can feature the key properties of glassy excitations. So in my talk, I will consider a Hamiltonian that has the same form as that of the SK model, but with vector spins having m components. So this kind of model is interesting because we take random fields that are randomly oriented. And this system is, for a given sample, it has no global rotational invariance, but is nevertheless statistically isotropic. So it allows us to study the critical behavior only without discriminating between longitudinal and transverse excitations, as one should do when there is a uniform magnetic field. We'll consider this model in two mean-field settings, one in a fully connected graph and the second in a sparse random regular graph. And in the first case, we'll consider Gaussian excitation, Gaussian distribution for the quench disorder parameters, whereas in the second case, we will consider rather mager distribution for couplings and spherical uniform distribution for fields. Now, these models have the advantage that there is, for spins with at least 3 components, a zero temperature spin glass transition in the magnetic field H. Now, with magnetic field, I will always, in the in the remainder of the talk, mean the standard deviation of the random external fields in this case. Okay, so let's go on. we can study the spin glass transition at 0 temperature through the control parameter H and relate it to the behavior of low energy Hessian eigenvectors. Now, the Hessian of this model can be again studied through random matrix theory in the fully connected case, and it's an instance of a deformed Wigner ensemble. In fact, indeed, the interaction matrix is perturbed by a diagonal matrix containing the local fields acting on each spin on the local minimum one is considering. Now, in this kind of random matrices, once one knows the distribution of the diagonal elements, it's always possible to obtain analytical formula for the spectrum. And secondly, for a wide range of distributions of diagonal elements, this model can feature both gapless spectra, so with vanishing frequency, the lower edge, and also phenomena such as localization at the edges. So they look like good candidates to represent the main feature we want to observe in a mean field model for glassy excitations. And secondly, since this model, we study this model in terms of the spin glass transition in a field, it's also a model that can describe the transition from a stable to a marginal glass. Now, let's start with the model on this network. Here I will give not an incomplete account of my results, but if you are curious, you can find more in the reference that is highlighted in this slide. So let's start with the results. What we did is that we obtained an analytical formula for the resolvent function of the energy Hessian, which is a self-consistent equation for in the function G. And from it, we obtained an analytical prediction for the spectral density through its imaginary part. We compare this analytical prediction with numerical data obtained by numerical delocalization of computer glass samples. And we also obtained by expansion close to 0 eigenvalue the behavior of the spectral density. And we found two scaling regimes. So at and just above a scale lambda star, a threshold lambda star, the system features what is known in literature as a pseudo gap. So it behaves as it has a square root-like behavior close to a gap lambda star. But instead, this system at far lower values than lambda star features a power law behavior whose exponent m-1 is equal to the number of degrees of freedom per spin. Spins are m-dimensional but are normalized to units, so the number of degrees of freedom is m-1. Now, the threshold lambda star, where there is this change in the scaling of the spectral density, depends on the distance from the critical point. So at the spin glass transition, the spectral density switches from a convex power law behavior, so from a finite spin glass susceptibility, to a diverging one. Now, so far, so good. I mean, we derived an interesting property of the spectral density, but we still don't know anything about eigenvectors. So to study eigenvectors in a mean field model on fully connected graph, the key quantity is the so-called inverse participation ratio. The inverse participation ratio is the fourth moment of the distribution of eigenvector amplitudes. So the inverse participation ratio can be related to the solution of the spectral equation here above. And according to its behavior in the thermodynamic, we can classify modes as localized or delocalized. Particular localized mode feature finite appears in the thermodynamic limit. The localized modes instead feature vanishing appears in the thermodynamic limit. an intermediate behavior between a scaling n to the 0 and a scaling n to the -1, intermediate behaviors are related to fractality or multifractality. Now, we were able to obtain an analytical equation for the quantity small I of lambda, which is shown in the left plot, and we compare this prediction with numerical data. So while numerical data agree very well with the prediction in the bulk, we observe deviations, significant deviations at the spectral edges. And this, in particular, we are interested in the behavior at the lower spectral edge, so in the limit lambda going to 0. This evidence is a hint of the presence of localization. And the plot on the right confirms this hint by showing that in the thermodynamic limit, so for the size n going to infinity, the IPR, in this case, the average smallest IPR is converging to a finite value. And as one lowers the magnetic field of the system, the IPR curves slowly converge to the critical black curve, which is vanishing in the thermodynamic limit and thus represent for this system, which is the Heisenberg spin glass, so 3-component spin glass, is a multifractal delocalized soft modes. Now, the mechanism behind this localization phenomenon is a mechanism that a la Bose-Einstein. It's known in random matrix literature as random matrix Bose-Einstein condensation. So essentially, soft modes, in each soft mode, a single component carries a finite weight, whereas the remainder of them are typically a value of the square typical component as a value of order 1/n. So there is a condensate component that is responsible for localization in soft modes. So what we did essentially is that we characterized this zero temperature spin glass transition in a field as a delocalization transition of soft Hessian modes. In our second work, we linked these properties for spin glasses to a model for structural glasses, which is the vector p-spin. So a p-spin model with vector spins. So this model has an Hessian that falls in the same random matrix class as that of the previous model. So it's a deformed Gaussian matrix, or in this case, more precisely, a deformed Wigner matrix. And so everything we learned about the behavior of the spectrum from the previous model, we can apply to this. So this model has at zero temperature an energy landscape that is 1 RSB stable at low enough energies, whereas it's marginal at high energies. Typical local minima in the 1 RSB phase are as those we obtained here. So a feature power law, convex power law behavior close to the origin, and localized excitations following the random matrix Bose-Einstein mechanism. And whereas in the 1 RSB stable phase, we also observe exponentially rare local minima that feature gapped spectra, that instead feature only the localized excitations. Finally, the marginal phase of the system is described by local minima that have a square root-like behavior of the spectral density close to the origin, and so divergent spin glass susceptibility and marginal stability. So we were able, in a fully connected midfield setting, to link the properties of excitations, or low energy excitations of paramagnetic spin glasses to stable glasses, and those of full RSB spin glasses to those of marginal glasses. Now, the next part of this talk will focus on sparse topologies. So here we did not obtain any analytical predictions about the spectrum of the model, but we only did a numerical study for the soft modes of XY and Heisenberg spin glasses. And because we were not able at that time to study the theory which consists in solving the spectral cavity equations for the resolvent matrix. So the first step we did to study this problem, was to obtain, the first step, natural step, we did this, but actually our research was very nonlinear, so we did this after we obtained the results. Okay, so the idea was that one needs to obtain numerically the value of the critical magnetic field at zero temperature. So
Flavio, 5 minuti.
Okay. So what we did is that we devised a discretization protocol for the sphere to discretize vector spins and solve cavity equations in population dynamics, obtaining the Delmeda-Taules line and extrapolating to zero temperature to obtain the critical field. So we measured the spectral density through the cumulative distribution function, and we found an exponent of the lower tail that is consistent with the value 4 predicted by the soft potential model. And this value, the behavior of the spectral density lower tail does not change at the spin glass transition in a field, at variance with what we observed in the previous model. Now, this result is seems to be robust among different vector spin glass models. So we obtained these results for the Heisenberg spin glass, but they were also observed for the XY model on a random error graph and for the three-dimensional, the Heisenberg spin glass on a three-dimensional lattice. Okay, now in the remainder, I will talk about mostly of Heisenberg spin glasses or random regular, no, only about Heisenberg spin glasses or random regular graphs. So in studying the property localization features, the inverse participation ratio is not enough because on a random graph, one has to link the concentration of weights of eigenvectors to the space, which in this case is the graph itself. In particular, we obtained that from the IPR that there is no change in the behavior of inverse participation ratio at the spin glass transition. It remains finite. So eigenvectors remains concentrated. So I'll skip the second part of this slide because I have little time. So about the geometry of soft modes, we recognize that when one has a concentrated soft mode, there are two possible scenarios. A single core mode where eigenvector weights concentrate around a single node, and a multi-core kind of modes where instead the mass concentrates around scattered cores in the random graph. So we measured numerically the number of such multi-core modes, focusing on B-core modes, so modes with two distinct localization centers. And what we found is that while in the paramagnetic phase, soft modes are predominantly single core, in the spin glass phase instead, soft modes are multi-core. That is, down to zero frequency, one can observe excitations that are concentrated in the weights, but are delocalized in the random graph. And so this, this property we found is very interesting because it's a kind of delocalization that was not observed in spin glasses before. And in particular, it's okay. So yeah, I don't know how many minutes I have, but maybe it's best if I draw the conclusions. So to sum up, The properties we wanted to test are the ones shown in this table, and we show that both models feature gapless spectra of low energy or low frequency excitations, that only the sparse model features a quartic law, but only the dense model features changes of the exponent of the density of state at the transition. Both models have a phase with localized soft modes. And finally, the dense model, we understand how it describes the emergence of marginal glasses. The sparse model, we still don't have a definite understanding of what marginal stability really means. Probably it's related to this kind of geometrical effects in the properties of Lagrange eigenvectors, but before drawing conclusion, it would be better to understand to find what is the right diverging susceptibility. In fact, since we observe that the exponent of the dot doesn't change at the transition, this also implies that the spin-glass susceptibility of this kind of models in sparse graphs at zero temperature remains finite. So it cannot capture, it's not a critical quantity for our phase transition. So perspectives, well, right now I will not do them during this postdoc because I'm studying very different things. But in the future, sooner or later, I would like to study excitations more. I have some unpublished results, but they are not satisfactory to me. And finally, I would like also to be able to learn to solve the cavity equations for the resolvent. And with this, I really thank you all that are listening, my supervisors and my collaborators. And finally, I acknowledge that during my PhD, I received financial supports also by Simons Foundations in the Cracking the Glass Problem project. So thank you again for the attention.
Grazie, thank you very much, Flavio.
Thank you.
Are there questions or comments?
I should.
Mm-hmm. Seems not at the moment. I have one, Flavio. Can you say something?
Yes, please. So who is speaking? Sorry.
Flavio?
Yes, Paolo, please.
Sì. Can you say something more about quasi-localization? In particular, how can you characterize it through the inverse participation ratio?
Okay, yes. So quasi-localization is a term that, in case of systems in real space, makes sense, and the quasi means that in real space systems, essentially the weights of the eigenvectors decay from the localization center, not exponentially in finite systems, but as a power law. And so the quasi is related to that feature, because like, for instance, in Anderson localization, instead, you don't have this kind of decay. Now, in midfield systems, like in the fully connected midfield system, there is no space, so localization is instead more should be termed more correctly as concentration, like how the weights of the eigenvectors are distributed among the nodes of the network. In the sparse system instead, the localization is related to space. Now, the inverse participation ratio does not account for the underlying network or space of the system. It just accounts for concentration. So it just tells how much it gives you an indication of how the mass of the eigenvector is distributed among the nodes, but it doesn't tell you anything about the geometry of this, the spatial profile of these eigenvectors. So it's a tool that is cool in the fully connected case, but it's rather limiting for more realistic kind of models.
Because the inverse, the inverse participation ratio is something that in the thermodynamic limit, when we increase n, either it goes to a constant, so you have localization. If it vanishes, you have delocalization, okay? But I wonder, but the way in which this quantity goes to zero with increasing n has nothing to do with quasi-localization?
So I think it's sometimes it's also a matter of how people term things, because yes, for instance, if it vanishes very slow, like n to the minus 0.1, yes, I mean, the mass is not really delocalized. I mean, it's distributed in a sub-extensive cluster of the components. But I mean, so like for instance, I prefer to qualify those kinds of excitations, so with a non-trivial exponent in the appear as multifractal or fractal, because as I said, in those kind of excitations, the mass concentrates instead of an extensive cluster, or in the case of localization, a microscopic or finite number of, a microscopic cluster consisting of a finite number of variables. It concentrates on a sub-extensive cluster that is diverging in size, because it's, even if it's small, if it's like n to the minus 0.1, it's still diverging. I mean, it's vanishing, and the effective number of components contributing to normalization is diverging, nevertheless. So I don't know, quasi-localization, I don't know if you're satisfied with my answer, but it's, in my opinion, the quasi is more about how it behaves in space than just these space agnostic features, such as the behavior that appear.
Okay. Thank you.
Thank you.
Okay. No other question or comments. In this case, ringraziamo gli speaker di oggi, Federico e Flavio, e
Grazie.
e poi la prossima sessione, l'ultima per quest'anno, sarà a giugno, come al solito il secondo giovedì. Saluti a tutti.
Ciao a tutti.
Ciao.
Bye bye.